If we start with theorem 5.3, how to get the derivative of a natural logarithmic function, and then turn that around to its inverse, which is integration, we get theorem 5.5, which tells us if we start off with 1 over x dx, then the antiderivative of that is the natural log of the absolute value of x plus some constant of integration. And then we expand that to take in the chain rule, and we get number 2 over there, which says 1 over u du equals the natural log of the absolute value of u plus some constant of integration. And another way of writing that second one is like this. If we've got u prime over u, then we end up with the natural log of the absolute value of u, again with that constant. So starting with the integral of 2 divided by x, that's 2 times too big. In other words, the numerator needs to be 1 for me to use the log rule. So what I'll do is pull the 2 out, and I've got this, which by definition lets me do the log rule. And so that will equate to this. And that one was pretty simple. Looking at the one on the bottom, notice that sometimes we've got to manipulate these things around algebraically. That's nothing new to us. Looking at this bottom one, though, it's kind of strange looking. And it'll take a second to realize maybe that this is not all that bad. First of all, I'm going to write it like this. Now, all I'm doing here is just swapping the second and third terms of the numerator. I can do that because we're adding. And at this point, you might catch on to what's going on if you didn't already know. And so then I'm going to take that and say, well, I can split my numerators and say, this is really the integral of x squared plus 1 over the x squared plus 1 plus x divided by x squared plus 1. Perfectly legal, and in this case, necessary. I can split those two integrals to where it looks like this. So x squared plus 1 on top and bottom just give me 1, which leaves me x divided by x squared plus 1 for my second integral there. Okay, it starts getting easier at this point. So I'm going to do a u substitution. And on the bottom, I could say, well, u would probably be this, which makes du 2x. Okay, going back, the numerator is only half as big as it needs to be. So I need to make that a 2x. And when I do, I have to pull out a half in front. And now then, this is in the form for my second integral of 2x over x squared plus 1, which is u prime over u. So when you string all that out, this is what you get. Now it goes without saying, if you start learning basic integration formulas and patterns, it's going to make this a whole lot easier. Second, even knowing those patterns, sometimes you have to say, okay, I've got something that looks kind of like one of those patterns I know. And that's a good place to start. And then you try and manipulate things around to where it looks more and more like that pattern. Number 3, if you can't find a u substitution, then you have to get creative sometimes and try trig, try multiplying and dividing. Any of those algebraic techniques that we've talked about before. That can get really interesting. Yeah, if you want to graph things, that's great. But number 5, you can always check your answer by just differentiating. See if you get back to what you started with in the integral. I've got to say, number 3 here is the trickiest one in this set of notes. When you first look at that, you're going, well, that looks like a multiply kind of thing, and I know we don't have rules for that yet. So what does it look like the most? Well, maybe a u substitution. So if we make u ln of x, then du would be 1 over x dx. Okay? So I could write this in this form. This is the same thing, just in a slightly different form, but it lets you see what's going on. Doing my u substitution, I've got 1 over u times du. And it just comes down to this. Now then, we still got to go back and substitute in what u really stands for. So when I do that, we get this weird result. Yeah, this is really it. The natural log of the absolute value of the natural log of x plus our constant of integration. Like I said, I think that's the trickiest one. Number 4. One of the things we've always done in trig is to say, okay, don't forget tangent is really sine over cosine. So I'll write it like that. And now a u substitution looks like it could come in real handy. And if u is cosine x, then du is negative sine x dx. To get negative sine x on top, I've got to multiply by negative inside and outside, which now gives us this form. I go back and replace u with what it stood for, and I'm ending up with this. And to wrap up this short set of notes, here are our trigonometric functions. You already knew a couple of these, but the rest of them come from the techniques just like we did with tangent.